Hey guys, what's up? Welcome to AlgoYogi. We are doing binary search series. We still have two more problems left. And today we are solving populating next right pointers in each node. Let's go to LeetCode and give it a read. Looks like a very straightforward problem. So you are given a perfect binary tree where all leaves are on same level and every parent has two children, and the binary tree structure basically the node definition is it's going to have the value, it's going to have left pointer, basically the left child, right pointer, right child, and there is this another extra pointer called next, and we have to do something around this next pointer, and let's find out what. So we need to populate each next pointer to point to its next right node. What is the next right node? What is the next right of 1? And during our binary tree series, we learned that there are two main ways of traversing over trees. One is BFS, which is level order traversal, and there is also, so this is BFS, you go like from left to right, so this is level by level, that is BFS, and then there is DFS, which goes like you come over here, then you basically trade and then come back, go to the right side, and then you traverse the tree like that. So we only need to do basically two things over here. First, traverse, and while traversing, just assign each of the node its next pointer. Fill that up. That's why it's called populating next right pointers in each node, right? So how about let's think about which traversal are we going to use. We could do any, but I think in this case BFS will be most useful, and the reason is when we are going level by level, we would have access to, when we are going level by level, we will have access to its right node in that order, right? And whenever we are on the last node, then we can check, because when you are traversing one level, you would know the last node is not going to have anything to its right, so that will be none. Okay, none or null, whatever. In this case they're saying null, but in Python we'll write our code in Python, which we will be placing none over there. So how do we do binary breadth first search? We're gonna have a queue. So we usually have a queue that is going to have the root in the beginning, so root, and then while queue we basically gonna take that queue's value into another queue. We can call it, let's say we can call it q2, or I'm gonna call it q-cur, and then assign that queue and have an empty queue again to fill things up. And then for node in this current queue, q-cur, I will be doing some calculations around this node. Depending on if it is the last node, then I will just have its next pointer to none. Okay, so I think you know now, like it becomes a really easy problem in my opinion, since we will be doing a BFS. You already know about BFS, and I think that will just we do have okay. I think the reason this problem is in binary search is because it involves a binary search tree or binary tree, although like since we need to populate each node's next pointer, then in that case we have to visit each node. So there is nothing about binary search over here. Like what can we do? That's what I think. If you think we could do it through BST, binary search, then maybe please comment down. But I think let's do a proper BFS, and while visiting on the current level, we go node by node and assign its next available node to its next pointer. And if it doesn't have the next node, then we just basically assign none to it, and otherwise keep check. If it has left and right nodes, then assign it to basically just append it to the queue. Okay, so I think it will be an easy solution. Time complexity here will be big of n. N is the number of nodes, and space complexity I think is going to be max in our queue, max 1 level, which is the last level, right? Which is the last level. And in the last level, if this is the height, so I think this space complexity max could go up to big of 2 to the power h, and I think -1. I think that's how it will be, because if you're calculating the number of nodes here, in this case it's 3 level, or you can say 2 level, then it will be 2 to the power 2. And I think this one, let's cancel that. This one is just wrong. I shouldn't have written that. So because it's a complete perfect binary tree, so this should give us the number of nodes. This 2 comes from the h. H is the height, which is this number of nodes from the root to the leaf node. Okay, so this and this makes us 2 to the power 2 gives us 4. 4 is the max number of nodes you will be storing in the queue at a given time. So logically that would be our space complexity. I'm gonna change the view here and write down our code. Okay, this thing we already know, so I'm gonna just remove this. Okay, I'm just gonna get rid of this. Okay, let's code it up. So let's write down if q is none, not q is none, sorry, root is none. If root is none, then I will return basically root. Otherwise I'll have a queue. Queue initially will have the root. That's what we begin our BFS with. First level is root. Now we're gonna start a while loop. While queue is not empty, I'm gonna assign this queue to current queue. That's what I mean. Current queue will take everything from our basically the queue that we just started with. Basically this is the original queue and this is the current level that I'm processing. First thing first, root is my level 0, you can call it, or level 1 you can call it, doesn't really matter, but like that's my first level, I would say. Now let's empty my original queue. Now what I want to do is I want to process all the nodes in my queue. Okay, so what I'll do is for node in queue, and I think what would be better is so that we basically know we are at the last element. So that would happen for I in range. So let's do it index traversal, right? Range length q cur. Now I'll have my basically current node, cur node, and next node. This will come from basically from here. That is my current node, and this will be my I plus 1. And I think what will happen is at the end, or maybe I think we don't have to do it like that. But we can just say if my I is equals to the last element, which is when I is equal to length minus 1. That means I'm at the last node, and this is where I can assign the next pointer dot I as next would be none, right? Otherwise next would be current I's next would be basically current QI plus. Okay, that's good. So either if you are on the last node, then the right pointer will be pointing to none. Otherwise, there will be a node that you want to assign to your current node's next pointer. That's it. There is one more thing that we need to do here is let's append the left and right child into our original queue so that we can process that level next time. So I'll just come out of this loop, and what I'll do is I'll take out the node would be current QI, and then if node dot left, then I want to assign this, I want to add it to my queue, original queue. So node dot left, same thing we'll do with, if you don't want to add the none values, you just want to add the non-none left and right children. So if right is present, q dot right, if right child is present, I want to assign it also to my, not assign, I think we're appending it to the queue. It's really hard to listen to myself sometimes. I'm just gonna throw this. Okay, yeah, I was just doing it to look cool, but it's messing up with my hearing abilities. Okay, whatsoever. Sorry, node dot right. Node dot right. Awesome. I think that is it. Now we can just come out of this loop and just return root. And if you see here, there are two queues. This is just the current level that I'm processing over here. If it's the last element that I'm assigning it basically the none as next pointer, otherwise next pointer would be the next available node in my queue, in my this current list or queue, whatever you guys want to call it. This is like an array or list, but I'm processing it like a queue because I am appending basically in the end, and then I'm accessing it from the beginning. So at the end of the day, these queues also have implementation done using list, right? Because list is an abstract data structure. I'm sure you know what an abstract data structure is. Abstract is like you're on this upper surface level, and the real implementation you don't have. You could go through the real implementation and change stuff and make like a complete different data structure. That's like an easy way of thinking about it. So I think this should be all of it. Okay, I am gonna zoom out and just give it a run, and hopefully this, okay, it's not the queue, my guy, it's the node. Yeah, these mistakes are common. All right, okay, let's submit it. Awesome. So accepted solution, and just let's make it look a little nicer, and that's it. Let's write the time complexity. Time complexity would be big of n. N is the total number of nodes. Okay, and space complexity would be big of 2 to the power h. H is the height. H is the height of the tree, and I should write it maybe like this. This is a better way of writing 2 to the power h. Okay, so let's go to AlgoYogi, mark this solved, and see you guys in the next problem. That is the last problem of binary search. There are a lot of other problems on binary search on LeetCode, but I think if you do all of these, then you become AlgoYogi. And what does becoming AlgoYogi mean? It means you are a cool tech bro. I'm just making it up. I mean, it's a good way. Like if you practice all of these questions, then I think you're in good hand to basically, if you went through all these like six easy problems and then a couple of 13, 14 medium level problem, that I'm sure if you did them like all right, then you should have developed an understanding, a comprehension about these binary search problems. And I'm sure like if you see other problems, you should be able to solve them, right? That's what I think. You don't have to do like thousands of problems of binary search to understand it, and you don't have to do a lot of them. It just, you do the right problems and you just develop that comprehension, understanding, and that I would say that formula to basically approach these binary search problems in future. Yeah, otherwise solving 2000 problems wouldn't do you good if you don't do it right. Yeah, sit down, open the problem, go through the description, develop an approach, write the brute force solution, and then next time you go through a different problem, binary search, then see, like, have you seen a similar problems and maybe develop like these patterns, because patterns are what will at the end of the day will help you categorize all these problems. So if you remember this cocoa eating bananas, like right from here, and probably like these I think all of these problems, these three problems, they were like in the same category. And I'm sure like even maybe more problems you can categorize. Okay, so bye-bye. See you guys later.